Good morning, everyone. Not sure what part of the world you're attending our webinar today. Welcome to our SEAM webinar series. I am Paola Vera, Managing Director of Technology and SEAM for the SEG, and I'll be the host for today. Thank you once again for joining us. We appreciate your attendance and we hope you find this session very informative. Today, we're going to highlight our ongoing research in our corporation, which is focused on the CO2 sequestration. Is an ongoing project. Mike is going to walk us through these advancements, and I'm pleased to introduce him as our speaker for today. So let me tell you a little bit about Mike before we start. Mike received his PhD from MIT and has held senior roles at Oregon State University, Los Alamos National Laboratory, and MIT. His research focuses on seismic imaging, reservoir characterization, seismic scattering, geothermal energy, and induced seismicity. He has led major modeling for SEAM, and he's currently our SEAM CO₂ technical project manager. Dr. Feller has published over 125 peer-reviewed papers and co-authored books on seismic wave propagation and borehole seismology. He's also a former president and editor-in-chief of the Seismological Society of America. So before we start, I would like to remind you all that your microphones are muted. So please send your comments or questions through the Q&A chat during the webinar, and we are going to address all of those at the end of the talk. So without further ado, I will hand it now over to you, Mike.
Okay, thank you, Paola, and thank you all for attending. I appreciate your interest in the work we're doing on CO2 as a part of the SEG Advanced Modeling Project. I don't want to spend a lot of time talking about the need for carbon sequestration. I'm assuming that you who are attending understand the need and know the issue of sequestration and the idea of geological carbon sequestration. This is just something from the IPCC, or the numbers are from the IPCC, about the challenge of carbon sequestration. The numbers are enormous. The amount of carbon that needs to be sequestered is huge. If we look at what has been done currently, or what's being done currently, we're in the megaton range. We need to quickly scale up to the gigaton range. It's a huge challenge. I went to a workshop on the gigaton CO2 sequestration workshop in Golden last summer, and I came back from it pretty discouraged by the scale of the magnitude of the problem. And this is kind of a brief advertisement, really, for a book that I read a review when I got back from Golden about this book, and I read it and I found it really encouraging. A book by Susan Solomon, who was involved in the discovery and understanding of the ozone hole. She goes through a number of scenarios of things that we have done to address environmental problems globally. Things like the things that are listed here. So this is a really good book. If you have concerns about whether we can meet this challenge, I think this book will convince you that challenges are big, but we can meet them. The outline of the talk is listed here. I won't go through it in detail. We're going to talk generally about the challenges, the models we're doing, the kind of simulation we're doing, the coupling going from the reservoir geomechanical simulation to geophysics, and then the geophysical simulations that we're doing. And I'll show you some results from the geophysical simulations. I put this is a cutout from a TLE article we published last fall about this project. So this is current. This article is current as of late last year. If there are things that you miss in my talk, you might want to look at that. It's in the December TLE. A very quick overview of the project. We built a pilot model, which is relatively compact. And the idea was to make it compact so we could learn from our mistakes, but also make it compact so we can do a good job of both doing the reservoir simulation as well as doing geophysical acquisition. So we built a pilot model, what we call the pilot model. We did two scenarios on it. One was the contained scenario where the CO2 was contained within the injection reservoir under a shale cap rock. Another one is where it's not contained. The fluid migrates up a fault into a reservoir immediately above the shale cap rock and then into a shallow reservoir at 500 meters depth. So I'll show you, we'll talk a little bit about those two scenarios. More recently, the bottom two slides are things that are figures of things we've been working on more recently. Our first geophysical simulations were fairly noise-free, and we realize that they aren't necessarily realistic or present realistic challenges for imaging of CO2. So we've been working more recently on introducing more complex near surface, doing simulations with a free upper surface. I'll go through what we're doing on that, the work that's underway now, to try to make the data a little bit more realistic. And then finally, we're working on a new model, which is instead of a land-based model, a marine-based model that's in a depleted gas reservoir. So that in this case, we will first simulate production from a gas reservoir, and then we will simulate injection of CO2 into two different levels within that reservoir. I need to give acknowledgement to our project participants who will support the project both financially and as well as technically. There are 8 project participants whose logos are shown here. I can't underestimate the value that they give into the technical work that's being presented here. This work would not be possible without their technical input. The project is really driven by the needs and desires of the participants. Okay, the challenges for CO2 sequestration, from the first slide we saw, we need to increase the scale by a factor of at least 100 if we're going to have a meaningful impact on the global climate challenge. Not only do we need to inject that amount, but we need to ensure and prove containment. Regulators will want us to show that we have contained the CO2 in the reservoir that we think we injected it into. Fault slip and fault reactivation is a critical issue for public acceptance. If we're generating earthquake activity, there's an issue about whether we're damaging the reservoir in any way, but also there's the risk to the surface facilities and the general negative perception of the public if we have fault slip. Cost is a huge issue. If we're going to do this on the scale we need to find a way to minimize cost as much as possible. And again, the last bullets there are sort of a subset of the first one. We need to do it on scale needed. That means at injection rates that meet our needs, as well as at the number of injection sites. And actually, over the large areas, volumes of reservoirs that we need to inject into in order to sequester the CO2 that we need to sequester. So the SEAM is a modeling effort generally. We've had several SEAM modeling projects, and this is the latest one. Why modeling is important for CO2 sequestration? Well, you can think of a lot of reasons, and a lot of them are listed here. No legal concerns. We can do all the modeling we want. It's safe. There's no public objection to this. It's cheaper than field experiments. The model is exactly known. We can modify it easily. We can investigate multiple reservoir geologies. We can modify the petrophysics. We can investigate different monitoring types and different monitoring scenarios, different acquisition scenarios. And we can control uncertainty through known noise. So it allows us modeling allows us, simulation allows us to investigate a range of monitoring scenarios and determine which ones work best and which ones are the least expensive. We're trying to find a sweet spot. Challenges for CO2 simulations. We are trying to do simulations that go from building a geological model to doing reservoir simulation and then coupled reservoir geomechanical simulation, and then finally transferring the output of those into geophysical parameters and doing geophysical simulations. So it's a big challenge, and we're learning. We're trying to learn from our mistakes, and there are a lot of challenges. The first one is model building. It's always a challenge for doing reliable model building. You want to build models on the scale that we want, with the scale of heterogeneity that's similar to what's in the Earth. Rock physics is an issue. Coupled geomechanics and fluid flow simulation has a lot of variables that are important to consider. Connecting the output of those to geophysical simulations is a critical issue. In the reservoir simulation issues, seal characteristics and failure mechanisms is something that we would like to explore. Borehole leakage is something that would be interesting to explore through simulations. We're looking at doing that with our current incarnation of reservoir modeling that we'll talk about at the end. Microseismic event activation and simulation are issues. Anything to do with the faults within the reservoir are issues. What do we use to properly characterize when the faults occur and how they modify the reservoir? How do we simulate then the seismic response to fault activation? And of course, CO2 chemistry is a big issue. So the focus of our project is to provide benchmark models and data sets for CO2 storage monitoring research. I'm not going to tell you the answers today. What the goal of our project is to provide data that allows individual investigators or their organizations decide which problems they think are most important for maybe a field that they're thinking of developing, and they could use our data to try to investigate how to address those problems. So we're trying to provide benchmarks, models, and data, improve overall simulation workflow efficiency, and particularly the issue of exchanging between disciplines, going from geology to reservoir simulation to geophysical simulation. And then ultimately, we would like to understand the value of information of different geophysical monitoring methods. You may draw some conclusions from what I show you today, but again, right now we're thinking that the understanding of the value of information is somewhat field dependent and somewhat organization dependent. So that will be up to our participants and others to take the data we've generated and evaluate value of information of different scenarios. When we do modeling, there are a lot of variables to consider, and they're listed here. One of the ones that was most adamantly asked for in the most recent set of simulations we're looking at is hysteresis. When you produce a reservoir, you reduce porosity and permeability, and you don't have recovery of that porosity and permeability when you re-inject. So hysteresis is an important issue, but there are a lot of other issues that are listed here that are important to consider when we do the kind of simulation we're looking at, multidisciplinary simulation. When we started the project, the participants got together and discussed what do we want for a model. And there are a lot of models, candidates that we could consider, and they're listed on the left side: sandstone reservoir, carbonate reservoir, depleted gas reservoir, depleted oil reservoir, environment onshore or offshore. We consider doing a digital twin where we take some existing reservoir and model it. Through a lot of discussion, we decided to start with a model we had a little leverage by building on a model that was used in a previous SEAM project called Life of Field. They had a pilot model that was compact and lent itself well to the work we wanted to do with some modification. It's onshore saline sandstone. The model was 12.5 kilometers horizontal dimensions by 4 kilometers deep. The reservoirs are a depth of roughly 2 kilometers, a little under 2 kilometers to a little over 2 kilometers. It's compact enough that we can do a reasonably good job of doing geophysical simulation on that with current budget, and allow us to investigate different acquisition scenarios and what we might get from those acquisition scenarios on this model. It has stratigraphic complexity. We use the best known rock physics to define the model, both initially building the model, but also then going back from the reservoir to the geophysics. As I said earlier, we're considering 2 CO2 injection scenarios, and I'll show that again in a minute when we look at the model itself. And we've done several geophysical acquisition types simulated, which we will discuss. There's a lot of parameters involved. And previous SEAM projects, a lot of them just worked out on the left side here. SEAM phase 1, where we were modeling the Gulf of Mexico, we started with the basic geology, and we went to the derived earth process properties that are important for geophysical simulation. But now we've added an enormous number of parameters, both from the reservoir response to flow and then the geomechanical response of the reservoir. So these are all the parameters that we're defining in our current model. Our next generation model is going to have actually more parameters. So there's a lot of parameter outputs, and then we have to figure out how to use those things to combine them in an effective and realistic way. This is a cross-section, an east-west cross-section of the model. The model's in a normal faulting regime. There are 2 faults that in this model. We're looking east-west. These faults both strike north-south. They're normal faults. One of them is sealed. The one on the left is sealed. The one on the right actually is open to flow in one scenario to flow across the fault. In another scenario, it's open to flow not only across the fault, but up the fault into the shallower reservoirs. There's the main reservoir, and it's starting at a depth of about 1.8 kilometers, going to about 2.5 kilometers. There's the reservoir seal. There's a 100-meter thick reservoir above the reservoir seal that fluid flows along this fault into in one of the scenarios. And then there's a shallow reservoir at 500 meters that's 100 meters thick. That again, in the fluid migration scenario, fluid migrates along this fault up into the shallow reservoir. I should say that in the model where the fluid migrates, the permeability along this fault varies over time with the fluid pressure and the stresses that are acting along the fault. The fault has the model has a lot of structural complexity, spatial variation and properties. This is just an example of some of the properties. V shale defines the rock type. The V shale of 1 means it's all shale, and V shale of 0 means it's all sand. When V shale is small, which is in this kind of turbidite, that's where the reservoir is. The reservoirs are in the center of the model. These are the horizontal and vertical effective porosities. And then these are defined on 2.5 meter thick intervals. So there's a lot of depth variation in the reservoir properties. The fluid flow and reservoir geomechanical simulations were done by SLB for the pilot model. We started out doing some testing, preliminary testing on a early version of the model, and then let it evolve based on things we wanted. We started out with the model that's on the left side, and then we morphed it into the model on the right side for various reasons as we evaluated the response of the reservoir to, in that case, it was mainly reservoir simulation, but with some one-way coupling, at least to look at how the stresses evolved in response to the fluid migration, injection and migration within the reservoir. 2 injection wells, one on the west side, one on the east side. The fault over here is open, so fluid can flow from the injector here across this fault into the central port of this anticline here. On the western fault, this is a side. This is a sealed fault, so the fluid that's injected here stays on this side of the fault. Injection period was 30 years. The simulation continued out to 100 years to allow the reservoir to evolve over 70 years after injection stopped. There's some other parameters here you can see that were used in the simulation. There is a SLB abstract from ARMA last year if you want more details about this. It's an expanded abstract. As I said, there were actually 3 scenarios simulated, but we've only worked with 2 of them. One of them was we called the contained injection, where again, fluid is injected west of the fault and east of this fault. Fluid can migrate across this fault, but it's contained beneath the cap rock on both sides. So that's our contained injection. Again, that's what everybody hopes for in the real world. What people don't hope doesn't happen is that fluid migrates. Fluid escapes from the main reservoir, and in this case, it's allowed to migrate up the fault and into this middle reservoir and into the shallow reservoir during the injection period. We also introduce something we call perm pipes, which is to simulate a type of cap rock failure that allows fluid to escape from this reservoir and go into the middle reservoir. And again, the idea is, can we, using geophysical methodologies, detect this fluid migration before it's catastrophic? And so that's one of the things that we hope that our data will allow users to do, is evaluate, does VSP, does EM, or does surface seismic allow us to detect the fluid migration before it actually gets very far out of the main reservoir. This just shows the injection parameters. The left side shows borehole bottom hole pressure. We capped it at 400 bars, and once it reached a pressure of 100 bars, then the injection rate had to slow down. The right side shows the injection rate, and what I've done is superpose. There's 2 different scenarios. One is the contained injection and one is the fluid migration injection, and there's 2 wells. And for example, this green one is the injector on the west side when fluid is migrating up the fault. And we actually never reach our 400 bar pressure, injection pressure in that one. And you can see that fluid, it continues to get injected for the 30 years. In some scenarios, we reached our pressure, and then fluid injection rate stops. This is cumulative injection. So when it's flat or near flat, we've reduced the injection rate because the pressure is capped. I put here, by integrating the gas density throughout the volume, what the rough estimates of the cumulative injection volume in this reservoir from 40 megatons to 50 megatons for the two different scenarios. We had to do a lot of testing going back and forth between the initial geophysical parameters going into the reservoir simulation model and then coming back out of it to make sure that we recovered the same thing, so that we knew when we allowed the reservoir to evolve and then went back to geophysical parameters that we were getting realistic representations of those parameters that we needed to define the geophysical parameters. I should say that the reservoir simulation did not output the geophysical parameters. We had to output the reservoir properties, which could then be used using raw physics to define the reservoir, the geophysical parameters. And this is just to illustrate the parameters we defined: VP, VS, density, intrinsic attenuation, and resistivity, horizontal and vertical. The seismic simulations are isotropic, just to keep it simple at this point. The simulations that we've done, these are all simulations that are done now on the pilot model. I've listed the simulations we've done and put in red the data that we've imaged. We've done 3D seismic on a baseline model, 2 monitor models, 30 years in both the contained and the fluid migration model. We did 2D surface seismic on the baseline and 3 monitor models, where we did a 2D seismic simulations on a monitor model at 9 years in the fluid migration model to see if we could detect the onset of fluid migration. We've done VSPs, and the difference between the VSP and these is these are about 45 hertz maximum frequency. The VSP is nominally 100 hertz maximum frequency. We've done gravity, and I'll show you some of the results from at least the imaging of the 2D and 3D seismic. I'll show you gravity results, 3D gravity. We collected downhole and surface DAS data from these simulations. We've completed recently microseismic event simulation, which involved first defining where the events should occur as a result of looking at the geomechanical simulation output, and then simulating events at the appropriate locations. There is discussion about doing noise for interferometry. Just to give you an idea of the 3D simulation, here's a map again showing VSAND. So again, the red area is the reservoir area. The 2 white triangles are the injectors, where we collected VSP data. The black triangle is another monitor well where we collected VSP data. The yellow dot is showing 2 shot gathers, one on the baseline model and one on the monitor model, collected at the same place. And you can look at this and see some differences in the reflectivity as a function of time in the monitor model. And this is a monitor model at 30 years. So again, we have a lot of shot data. Shots were placed at, again, these are the shot spacing. The red dots are the shots in this model. There are actually receivers throughout the model covering the entire model, and those data are all available. This is the image. I should say that the simulation and imaging, seismic simulation and seismic imaging were done by Advanced Geophysical Technology, and I've listed them down here, Weijin and Zhu, who did the work on this for us. So they did both the simulation and the imaging. This is a 2D cross-section, east-west cross-section, which is sort of our favorite cross-section to show of the 3D migration in the contained injection at 30 years. We migrated this with the baseline model, so just to have an imperfect velocity model for the migration of the monitored data. So you can see there's some pull down in these lower portion of the reservoir, resulting from using the incorrect velocity model. But you see we get a pretty good model or image of that, and it's certainly unrealistically good. This is a schematic just to show we did 2D simulation, which is really 3D simulation with using lines of sources and lines of receivers. The lines here show the sources and receiver positions along those lines. We also collected then VSP data. We did 2 simulations of these shots and receivers, one at 45 hertz and one at 100 hertz. The 100 hertz was aimed at the VSP data, but we in fact collected both surface and VSP data for all of these simulations. So those data are available. But the idea was you could do a sequence of walkaway VSPs from these wells or 2D imaging along these lines. And I'm going to show you a 2D image along this line, both from the 3D data and from just the single line of shots. Here, the right side is the 3D image that I showed you previously, again, migrated with the baseline model. The left side is the 2D image again, just using a line of shots simulated in 3D. So we have 3D wave propagation effects, but it's been migrated as a 2D migration. And you can see the migration is actually pretty good. I mean, there are details that are not prominent, not present in 2D, but the general features of the migrations are not too different. So it shows some hope that 2D acquisition has some benefit. And again, users can experiment with these data as their own liking to investigate different scenarios. As I said, these images are certainly better than might be expected in real field situations. One of the things that the group wanted to do was to investigate what happens in a more realistic situation. These simulations were done with an absorbing upper surface, so there's no surface waves and no interaction between the scattered wave field with the free surface. So more recently, we've been looking at what happens if we first make the near surface more heterogeneous. And you can see this is the model that we've used, that I've shown you the results for so far, called the original model. And now we've introduced some near surface heterogeneity that increases from west to east. The idea is to see if the image degrades going from west to east. But also we're going to do 3D simulations with this with an absorbing upper surface. And just to give you an idea of what this will do, Joe, Stephanie, and I have looked at probably 50 or 60 models and done more than 100 migrations in 2D, trying to evaluate different realizations of near surface heterogeneity and how they influence the quality of the image we get. And I'm only going to show you the model that we've landed on, and that's this one. But I'll show you first some gathers in this model, as well as some images that we get in 2D. Because 2D, we can do a simulation and imaging overnight, pretty much. So here is a gather, and the shot is in roughly the center of the model for these gathers. So these are gathers all at the same shot location. This is the original model with the absorbing upper surface. So the data are really clean. And so you're not surprised why we got such a good image. If we just add a free surface, you can see the data get notably degraded. You know, for one thing, you see the surface wave propagating along and really making a mess of the near offset portion of the data. But you can also see even the further offset part of the data are not very good. So we could just take the model and add a free surface. And I'll show you an image where we've done that. But if we add the noise and go to an absorbing upper surface, so all we've done here is just added that near surface heterogeneity, the data quality degrades, but you can still actually see some good continuity of these reflectors, even at the near offset, even with this noise. But then when we go to the noisy model with the free surface, we can see that the data quality goes quite a bit. And you can see where the noise has really interfered with reflectivity on the eastern side of this gather. And in the center of the gather, these reflectors are poorly shown in this. So our plan is to go to 3D with the model, with this scenario, free surface and the noisy model. But with 2D, here's a series of images that we get doing the same shot gathers that we did before, but now we're using 250 shots actually simulated across this model. This is the original model with the absorbing upper surface in 2D simulation, 2D imaging. So this is as good as we could expect to get. The image is pretty clean. Again, migrated with the baseline velocity model. The image is very clean. If we just add a free surface, it degrades quite a bit, and you start getting a lot of artifacts. Artifacts get amplified in the image. If we add the noise, the image again degrades going from here. So all we've done is absorbing surface in both cases, but added the near surface noise to scatter some of the outgoing wave field. But now if we add not only the noise, but the free surface, we get a lot of interaction between the noise and the free surface that degrades the image quite a bit. We see that there's some areas where there's multiple reflections near the surface that propagate into the image at depth, and the image degrades quite a bit. So the path we're on right now is to pursue a 3D image with simulation and imaging with this model, having noise and the free surface. And we're just about ready to pull the plug on that simulation with AGT and have them proceed with the simulation and the imaging. Gravity, Joe Stephanie at Chevron did some gravity, 4D gravity, Surface gravity, as those of you who work with this, you probably know that surface gravity gives a response, but the response is too small to be observed in the real world. But this is the surface gravity response. On the west side, I've shown just where the gas is. It's kind of a radar X-ray of the gas distribution as a function of horizontal position, and you can see the two gas clouds. And this is the contained injection. So you can see the gravity signature is there, it responds to these gas clouds, but it's not big enough that it would be observed in the field. So Joe has also calculated 4D gravity at these three wells. These are the two injectors, and this is the monitor well. These data are available. And for example, this black, you see a decrease in gravity. This is at the eastern injector, so it's at this injector. So as you go with depth and you get near go down towards the top of the reservoir, you have a decrease in gravity, and then you have an increase in gravity. So this is both vertical and radial gravity in the three well bores that are available to use to evaluate. The signal is still small. I'm going to spend a little time talking about the microseismic simulation, and maybe more time than others might, just because that's an area that I've been really interested in throughout my career. So we wanted to do simulate some microseismic events, and we started out with sort of a listing of the things we might want to do with microseismic data. Some of it just testing methodologies for evaluating data, others sort of coupling analysis of the microseismic data to what's going on with the geomechanics. And I put just a couple of papers here, a couple that I've been involved in, looking at moment tensor inversion challenges, for example, where the velocity is poorly known, which is usually the case. And so our hope was to provide data that could be used to investigate moment tensor inversion in areas where the velocity model was misspecified. In other words, we have a poor velocity model, but also work that's been done at Los Alamos and then by my collaborators in Saudi Arabia, looking at network design, both for event location, the Los Alamos group, and then the moment tensor inversion by the group in Saudi. So these are things that people are actually doing now. There are papers written about all these topics now, non-double couple events, caprock integrity evaluation. People are interested in ground motion. So these are things that we wanted to build a microseismic event data set that could be used for as many of these objectives as possible by our users with minimal modification of the data. So we've decided to simulate two sets of events. One set of events, these are the east-west cross-section showing the locations of the events, where at each point, we do 6 simulations. And the 6 simulations are for each component of the moment tensor. And this will allow us to have data that users can use to specify their own moment tensors. So we don't have to argue about whether you want to have a double couple event or a CLVD or some other pure tensile event or an isotropic event. You can take these data and sum the results from the different moment tensors to get anything your heart desires. And these were done in 3 different velocity models. In the model with fluid migration. So the baseline model, the model at 9 years and a model at 30 years. So we could have data that are calculated in 3 different velocity models. So you could evaluate the effects of, say, location and moment tensor in areas where the model is poorly known, misspecified. So that's one set of events that we've simulated. 3 velocity models, 6 simulations at each location to give 6 components of the moment tensor for each point on this plot. And then we did another set of events where we actually specified the moment tensors. And we generally specified the moment tensors to be consistent with normal faulting along the faults that you see, the eastern fault, which dips to the east, and the western fault, which dips to the west. In this case, the geomechanics actually said, because there were higher pore pressures over here, that there was more likelihood of faulting off the fault as well as near the fault. These tended to want to stay more near the fault. The geomechanics actually gave us enormous numbers of locations where events might occur. We had to pick a handful to simulate. Again, these are all pure double couple events. They aren't all perfect fault slip along this fault. We modified the moment tensors a little bit so that the orientation of the slip varied a little bit about these faults. But again, simulated on all three velocity models. One of the things we wanted to do that I was worried about was making sure that we properly communicated our moment tensors to AGT. So we spent a fair amount of time actually working with AGT to make sure that our definition of moment tensors was consistent with theirs. And this just shows we used a simulation of the homogeneous medium. This is the distribution of amplitude and polarity as a function of position at a ray near the surface for a pure thrust fault located at depth in the model. We have downward motion on one side of the fault and upward motion on the other. And we have a nodal plane that you can see here. This is what Aki and Richards would predict we should get for amplitude and polarity. This is what we got by our calculation using a reflectivity code, which can only deal with simple models. This is what AGT gave us. The comparison is quite good. And actually, if we look at waveforms, the waveforms are almost a perfect match between our reflectivity calculations and AGT calculations. So we really convinced ourselves, Lijian and I spent a lot of time working together to make sure we had done this correctly, just because we wanted to make sure that if we were going to spend all this effort to do it, that it was done well. Likewise, we can look at S-wave radiation, again, using Aki and Richards. And we did this to, again, make sure that the moment tensors were properly inserted. A quick look at some of the waveforms. I'm going to show you two waveforms from two events. And actually, the events, we're just going to look at one component of the moment tensor for an event that occurred here and a receiver that's up here. So the propagation path is not going to be a straight line between source and receiver. It probably goes somewhat through this eastern deeper reservoir, but it definitely goes to this eastern shallow reservoir. And then we have another event over here, this recorded over here. It does go through the eastern reservoir, and it probably doesn't go through the shallow reservoir. But again, the idea was, can we look and see what how the waveforms change with time for three different models: the baseline, the 9-year injection, and the 30 years. So in 9 years into this injection, the CO2, this is a 30-year plot. So the CO2 is not actually, there's no CO2 up here. It just barely made it up to this area. It's not gotten to this region. There is CO2 here, but not very much. And then at 30 years, actually, this is the 30-year plot. So you see there's a lot of CO2 in the shallow reservoir. So we have a baseline, we have 9 years, and we have 30 years. So I'm showing now, again, source location, receiver location at the baseline, 9 years and 30 years. And then I've overlaid them here, and you can see that there's an evolution of the traces. The first arrival was delayed successively as we go from the baseline to 9 years to 30 years. And the coda, this is the P coda, varies with time as the injection continues. So this is what we'd hope to happen. And we hope that this provides a data set that's rich for both investigating, for example, location and moment tensor inversion, as well as other things. The other event actually shows a bigger change, and we're actually looking at an up motion here. So again, the baseline, 9 years and 30 years, and here I've overlaid them, and you can see that between 9 years and 30 years, there's a significant delay in the P wave arrival time due to the presence of CO2, both mainly in the deeper two reservoirs, and you can see that the character of the waveforms changed over time. So these data are available to our users and hopefully to the wider community with time. So we've described the simulations we've done on the pilot model, the simulations that we're getting ready to do on the pilot model, where we will modify it to include near surface heterogeneity and a free surface. We're also undertaking a new model, which is a marine model, where we're going to first, it's similar in structure to the model we've been looking at, except that we'll have a near surface layer of water. But it's going to be, it's going to be a gas reservoir that will first be produced at the anticline, and then we'll do injections in a deeper part of the eastern reservoir and a shallow part of the eastern reservoir. These simulations are underway. This is a reservoir simulation that was done by Chevron without geomechanics. SLB is now in the process of doing fully coupled reservoir geomechanical simulations of, again, this long scenario that will have gas production and then CO2 injection. So it'll be a depleted reservoir. So we're hoping to get that done by the end of the project later this fall. So there's a lot of use of these data. I haven't really tried to tell you what conclusions we've drawn from the data, because we've mostly been working on generating the data and making them available to participants and some of their collaborators. but there are things that users could do with the data, for example, in measuring value or information, looking at which tools work well independently or in combined with which acquisition geometry, what is the best mix to get a good interpretation of the data, streamlining workflows long-term to do better simulation in the future. Again, I think our second simulation model, this is going to be a much better simulation because we've learned some things from our first simulation. And, again, a work zone for testing things. You could take our models and modify them, either modify the rock physics, or you could even take the model and modify the geology a little bit and do new reservoir simulations and then couple that into the geophysical simulation. Finally, there's plans to start a second version of this project called CO2.2. Bill Abel is actively engaged in discussion with prospective participants about this to look at what things would they like to investigate. I think one of the things they would like to do is do more work on the data that we've collected. We've done a lot of time in imaging the data, but we haven't spent a lot of time actually using the data to evaluate what we can learn from the reservoir, about the reservoir from it. There's interest in that, but as well as investigating other environments. Again, the actual content of the project will be defined by the users, but can we extend the learnings and can we learn more from the data we've got, but also can we investigate other regimes? So finally, if you want to learn more about the project, I guess you can scan this QR code. It will take you to it. We're hoping that this project will launch in the fall. The current project is going to end in September, end of September, and we would like to have the next project ready to go. So this QR code will give you take you to information about the project. And finally, there's other SEAM projects. Another SEAM project that's going to start as well, looking at the land-marine interface, acquisition issues there, as well as projects in the past that there are data available that you can purchase from the SEG website. So with that, I hope I've left enough time for questions. I'll let you take over and lead the question and answer session. Thank you.
Thank you so much. Thank you, Mike. That was great. Okay, so somebody's asking if would it be possible for universities to have the data for free. Maybe I can take that one, Mike, if you.
Okay, that'd be better if you did.
If you think. Yeah. So, right now we are under confidentiality period. Let me put my camera on. So we usually allowed our participants to keep that right because it's a fully sponsored project. After 2 years of the project completion, these data sets will be available for licensing. They will be available for the industry and the academia. The academia will have a much smaller fraction of a cost. We are actually considering, I cannot promise you it's going to happen tomorrow, but we're working with our SEAM board right now to analyze or evaluate is the right word, to see if we can come up with a teaser, perhaps in 2D, that could be in open source or at different levels or at different tiers for more accessibility before the confidentiality period is over. So stay tuned and we'll keep you posted via website. If you have any more questions, again, use our link and the contact form is there on the Q&A section. And we'll be happy to address your concerns. Okay, we have a question from Jake Lee. Could you elaborate on the difference between time-lapse pilot and the CCUS pilot model?
We have two models. One is the pilot model, which is we call the pilot model, which is the land pilot model, which we've done time-lapse data acquisition on. So 4D acquisition, both 2D and 3D, as well as seismic and EM, or seismic and gravity. We're discussing about doing EM acquisition. The new model we're working on is a marine model, and that will also have time lapse. That will again evolve in time. We'll first produce it, and then we will start injection. We're still in discussion about exactly which the acquisition we will do on that model. I think there's discussion about calling the baseline the end of gas production would be our baseline for the CO2, and then we would do a sequence of monitors following the injections into the deeper reservoir and into the shallower reservoir. But we still want to look in more detail at the output of the reservoir simulations before we decide exactly which times we want to do the monitor simulations on that model. So that work is in progress, and we hope to have it done by the fall.
We have another question from Colin Sayers. Hi, Colin. To what extent Are geochemical interactions between CO2 and rock included?
Oh boy, I was afraid somebody would ask that, and Colin would be the one.
I knew Colin would.
Yeah, Colin, it's not included in the simulation, unfortunately. I don't think anybody's got right now, and I may be wrong. At the time we started this, we could identify geochemical simulation codes and separate reservoir geomechanical codes. So right now, there's no coupling between geochemistry and reservoir and geomechanics. Joe did some, and again, I don't know if Joe's on this talk, but it would be better if Joe could answer that question. He made some adjustments for geochemistry when he did the rock physics, sort of after the reservoir simulation was done, to try to incorporate some appropriate geochemistry into the rock physics. But if I said anything about it, I would say it wrong. So if Joe's on board and you can put him on, Paula, that'd be great. If not, we'll have to work with you, Colin, to get you a better answer. Or you can contact Joe yourself. Joe Stephanie, who I'm sure you know.
I don't think he's connected right now. And this is also a topic that we are considering to expand on the CO 2.2 as well. Of course, subject to decision from the participants. All right, we have another, I think we have time for a few more from Hassan City. Are we over-engineering the CO2 injection projects through our bias in managing petroleum gas?
Oh boy, that's a good question, and I'm not sure I'm the right one to answer that. You know, I think the issues in petroleum CO2 injections are maybe a little bit different. You know, you're worried about sweep efficiency. You know, you're trying to push as much CO2 into the reservoir to get the petroleum to migrate to your production well. So it's kind of a different thing, and you actually don't worry about loss of CO2. You know, in CO2 sequestration, there's a lot of issues that regulators may ask about. You know, not only can you prove containment, but can you prove you know where the CO2 went, as a way as sort of a collateral way of proving containment. If you know where the CO2 went, all the CO2 went, you could prove that it's contained, or prove that it's not contained. So I think the needs are a little bit different. You know, of course, there's, you know, years and years of experience in enhanced production using CO2. So I think we may be biased by that. You know, the experience we have and the tools we have built are based on that. So certainly it has an imprint on what we do. But I'm not sure. That's a lot of words, maybe not answering your question, and I apologize.
I think we have time for one more from Yegbook Lee. I was wondering if the geometry of this model is very similar to the SEAM pore pressure model or time-lapse pilot.
Yeah, it's definitely not the same as the pore pressure model. The pore pressure model, the SEAM pore pressure model was a deep water Gulf of Mexico. There's salt. So it does have turbidites, and so some of the infrastructure that was put together for building that model, actually the phase one model, which sort of morphed into the pore pressure model, were used to build this model. But it is very similar to the life of field model, because we borrowed it at the beginning. I think Joe built that model, and then he sort of borrowed what he had built and modified it appropriately for this model. And I think that model I think is publicly available. But the pilot, the life of field pilot model, I think is publicly available. But again, it'd be better if Paolo would speak to that than me.
Yeah, they're both open for licensing, both the siliciclastic and the carbonate life of field. We use, the input for this one is of course the siliciclastic model.
Yeah, this is not a carbonate model. So, but yeah.
Okay, I think there is one last question that we may be able to take. I'm not sure if we're going to be able to fully answer that one right now, but let's give it a try. Can you elaborate on the petrophysical, I think, model to compute dry bulk modulus and sensitivity to pressure?
Oh, wow. You know, that's another question for Joe. We had a lot of discussion about, computing dry bulk modulus. I was thinking of static bulk modulus. You know, we had issues not only with bulk modulus, but the dynamic and the static are issues. And of course, there's a lot of discussion about that, both based on lab data and theory. The dry bulk modulus, I think I would defer to Joe on that. Again, there's a lot of details And for those who are participants, and I guess ultimately his report will be written or available. His report is very comprehensive. Unfortunately, it's not publicly available, but I'm not really qualified to give a good answer to that question. I'm sorry.
Okay. Any last minute question before we wrap it up? I would say probably not. So I'm going to personally say thank you, Mike, for this wonderful presentation. It's always great to see you present. And thank you, everybody, for joining us today. As a reminder, we will make this video available on our SEG past event page. So once we finalize it in the next few weeks, it will be available for those who missed it. Thank you all once again, and have a good day or good rest of the evening. Thank you, Mike.
Thank you, Paola.
Bye-bye.
Bye-bye.